next week, not this Thursday and Friday, but the 22nd and 23rd. So you will be with me 5th and 6th period, Thursday and Friday of next week. And those of you on distance, I'm not sure how they're doing it for the juniors on distance. For the science test, it's juniors and seniors that have to take it. So James will also have to take it. Those of you that are sophomores will be with the substitute, or if you're at home, there'll be something for you to do at home. God bless you. God bless you. My plan is to do a little bit of the practice test, show you the format of the test and a couple of glitches that I noticed. When I just went through all the practice questions last night in anticipation of what I already figured was going to happen, and Mr. Moreland told me we're going to do the test. So this morning, but the state test, there's a couple things you have to notice, and I'll just try and show you that next week. Okay. So it's not really going to change that much, other than we won't have regular class Thursday and Friday. So law of conservation of mass, we need to do right now this physical change. So I'm going to do sodium hydrogen carbonate and water. That's a fancy name for baking soda and water. And to do this activity, we went through all the colors yesterday, right? We got the red in the acid, the purple in the base, teal in baking soda, red in acetic acid, and green in the water. Perfect. So I am going to put I know what I'm going to do. I'm going to do this. This one. That one. Physics questions. Plastic bag, and I'm going to put a scoop of baking soda and a pipette with water in it. So remember, water is the universal solvent. Water dissolves lots of things. And get it to go down into the bowl. There we go. And sodium hydrogen carbonate baking soda is an ionic compound, polar solvent, ionic compound. They're going to dissolve, right? So I'm going to put the pipette in the bag and then close the bag. And then I have my handy dandy balance here. Zeroed it. I'm going to put this into a cup only to help it all stay centered on the pan. That's the only purpose of this. And you're going to type in there 15.26. Okay, so that is the starting mass, and you're going to predict what's going to happen. Is the mat when I'm going to invert the pipette, the baking soda, and you're going to tell me, will it increase the mass, decrease the mass, stay the same? Yes, 0.26. And again, I don't know why this is all. Hang on, let me do this. Beep, beep. Oh my gosh, there we go. Increase, decrease, stay the same. You make a prediction. Okay. Who thinks it's going to get heavier? 2 people. Who think it's 4 people? Okay, 4 think bigger. Who thinks it's going to get lighter? 3 people. And a whole bunch of people don't care. Good job. Okay, here we go. You guys are terrible. Why? Nobody's laughing. Come on, you guys. So I'm going to go ahead and invert this. Squeeze out the water. Nothing much is going on. It's just dissolving some of it. I'm going to put this back in here. And voila, it still says, any guesses? It still says 15.26. You want to see? case you don't believe me. Whoop. Why is it doing that? What the heck?
Well, just like 20 people on the industry was very.
No, you can't. It says 15.26, I promise. That's poopy. Oh, there it was. You saw it. I saw it. Okay. Ooh. Come on, you can do it. Let's see what Wi-Fi I'm on, just for the heck of it. That's off. That's strange. All right, so that was a physical change. Stay the same. Next one we're going to do is chemical change. This time we're going to do 2 bags because it's a little trickier. So I'm going to switch back to that and unpin that. Oh, I hate doing that. I don't know why I do that all the time. There we go. Okay, so the chemical change part is the classic volcano reaction. So let's just go over a couple other things though first. Yesterday we looked at hydrochloric acid and we looked at sodium hydroxide. Recall that those are both ionic compounds. Acids have hydrogen. Bases have hydroxides because when they go into solution, they dissociate, they come apart. Okay? And so we end up with sodium and we'll end up with chloride as well. Okay, little charged pieces. And this type of reaction makes sodium chloride, table salt, and hydrogen hydroxide, which of course you would normally call, anybody? 2 H's and an oxygen. What is that? Are you guys out there?
Water.
Water, thank you. Killing me. Okay. So when this neutralization reaction happens, and we're going to get into this more in coming days, sodium chloride forms, the metals always first, hydrogen and hydroxide, which of course is really water. Okay. And so this is a neutralization reaction. It's also called the double replacement reaction. What we're going to use instead is an acid, acetic acid. Okay, it's the hydrogen ion. Remember, acetic acid is the fancy name for vinegar. And the acetate ion we supposedly learned previously. And then baking soda is sodium hydrogen carbonate. Okay, and sodium has a +1 charge. Everybody knows that. And then hydrogen carbonate is also called the bicarbonate ion. And when we put these together, we end up making sodium acetate. And we end up making something else. So here's the thing. What happens when vinegar and baking soda go together? Did anybody do a volcano in elementary school? Huh? It bubbles, right? It foams and bubbles. Okay. That's because what gas is forming? Turn to your neighbor to see if they know. What kind of gas forms? Oh, it's carbon dioxide. There we go. We already got the answer. So we've got ourselves some CO2s. What ends up happening is carbon and 2 oxygens go off as a gas. And then what we've got left over is the hydrogen over here. Okay, the hydrogen here and this oxygen. What's 2 hydrogens with an oxygen? Water. Okay, so we're going to make sodium acetate, which dissolves in water, and CO2 gas. So those bubbles are hard to catch. It's the hardest thing of all is to measure the mass of a gas. It's complicated. It's not impossible, but it's kind of hard. And it was really hard back in the 17 and 1800s when they were trying to do that. So those bubbles I'm going to capture by using a double bag. Hopefully it will work. And I'm going to put some baking soda in here. Shoot. No. Oh my gosh. Okay. Let's get out of that and unbend that. Too many things to remember. Okay, baking soda. I'm going to throw in some universal indicator just because it's kind of fun to look at. Sometimes I'll put that in the other corner. And some vinegar. So the vinegar is in this pipette. And I want to make sure it doesn't touch it. Yeah. I'm going to put it in the baggie. And you can see the tip of the pipette is turning red. Or I can see it anyway. Take the air out. Zip it tight. And then I'm going to wrap that up and put it in another one to try and make sure the gas stays in. It doesn't always. Okay. And make sure this is good. Good. $19.20. So this time, oops, I forgot to put in the answers here. 15.26, it stayed the same. And that means it's conserved. Okay, and then 19.20. Okay, same thing. Increase, decrease, stay the same. Make a guess. And then I'm going to squeeze them together. Okay. Everybody got a guess? Who thinks it's going to go up? Okay, some of you. Who thinks it's going to go down? Some of you. Who thinks it's going to stay the same? Nobody? Wow. Okay. So very obviously a chemical reaction is happening. I can tell that because of the sound. And and the indicator didn't mix in. So bubbles, and it's a tighter bag now. And we're going to see how we did. Okay, so it did go down slightly, 1914. But it didn't go down very much. And I could certainly, I didn't do this earlier. I'm going to burp the bag, see if I can get the rest of the CO2 out of there. See how much should have changed. There it is. So CO2 is a little denser than atmospheric. I don't know if it's going to make a difference or not, but let's find out. Not a lot, 1912. So it did lose some more mass by letting the CO2 out. So some of the CO2 definitely escaped. So it did get lower. It's a very small difference, though, 0.067, 19.2. We can also do it this way. So 19.14 divided by 19.20 times 100. See how much we still have left. It helps to turn your calculator on. just in case you didn't know. So we still have 99.7% of it still present. So, if you're doing an experiment, that is hardly any kind of a loss, very, very small amount. We still have most of it left. So we can say that matter is conserved, aka stays the same. In physical, whoop, that's not physical, there we go, and chemical changes. Okay, so that is the gist of the first law, which is actually stuff we've already covered previously. Good so far? Questions? All right. So I'm going to go to my PowerPoint, and you're going to just type in a little bit of notes down here, and then you're going to submit this before we leave for the day. So here we go, really fast. Oops, that's physics. Let me get rid of that. Also, one other thing before I forget, calculators. You need to have calculators for the next several weeks. So please, if you're not in the habit of bringing a calculator, be sure you do. I do not allow you to use your phones. Okay. So we're going to talk about proportions, which is another kind of fancy way to say fractions, which a lot of people don't like, but it's really not hard stuff. Okay. Just a little bit of division, super easy. So the proportion of candles to cake on this birthday cake is 4 candles for 1 cake. And in proportions in math, you can use colons, you can use fractions. There's different ways to do them. There's 2 laws that we have to talk about, law of definite proportion and the law of multiple proportions. And I'm going to talk to you about the guys that found these laws or are credited with these laws, but the only one you really have to know is Dalton, and you don't have to know the dates. Just know it was a long time ago, as usual, okay? So Joseph Louis Proust was a French chemist in the late 1700s, early 1800s, and he came up with what's termed the law of definite proportions. And in a sample of any chemical, pure chemical, that's a big, big, big thing. In any pure substance, the proportion of the elements by mass stays the same. Okay. If we're looking at the mass, like I did on this lab and got numbers, okay, those proportions should stay the same. Again, it has to be a pure substance. It can't be a mixture, because by definition, mixtures can vary. You can have 1% milk. You can have skim milk that has no fat in it. You can have whole milk that has 3 or 4% fat in it, right? So mixtures can change, but in pure substances, the masses stay constant if you divide them, constant ratios. Some books call this the law of definite composition. If you're going to have a particular compound, you definitely have to have it composed this way. So that's another way to think of it. Our book has 2 really strange pictures in it. One of the pictures is a picture of some blue jean material in a beaker of water. And, all of us have seen jeans wet before. They just get kind of darker, but it doesn't do anything, right? And of course, the formula for water, H2O, has to stay the same. Okay, and it follows the law. If, which they did, I don't know if you guys remember when I did the Hoffman apparatus experiment and separated the water into oxygen and hydrogen, and I got it to the hydrogen to go whoop, and the oxygen, I don't remember if the splint relit in this class or not, but you can measure the mass of a gas. It's not easy, and they escape. But if you measure the mass of the hydrogen and oxygen in a sample of water that you separate, it always comes out in an 8-to-1 ratio. Notice this is really critical to getting these problems right. Oxygen is first. The 8 refers to the oxygen. Hydrogen is second. The 1 refers to the hydrogen, right? And the 2 is a little colon there. That is a simplified fraction, if you will, or proportion from the actual proportion. So hydrogen is element 1, it has 1 proton, but it has a mass of 1 gram per mole. We're going to find out about what those mean more. Oxygen is 15.99994, so basically 16. So if I have 2 hydrogens, that's 2 times 1. 1 oxygen, that's 1 times 16. 16 divided by 2 is, of course, 8 over 1. Everybody understands that, right? So they didn't necessarily have perfect numbers like this when they were doing the experiments, but every time they divided the mass of the oxygen by the mass of the hydrogen, they kept getting 8. Okay. There's another substance that's also made of just, and this doesn't mean that those are the number of atoms, right? Because you know it's 2 hydrogens to 1 oxygen, not 8 oxygens to 1 hydrogen. Another substance that has only hydrogen and oxygen in it is hydrogen peroxide. And some people use that to get highlights in their hair. Some people use it for like cleaner. Hydrogen peroxide can be used as a disinfectant. There's all sorts of things. It also, again, is only hydrogen and oxygen, but this time it has different proportions and different characteristics. So this bizarre picture right here is a piece of that denim stuck in hydrogen peroxide. And notice instead of being darker because it's wet, which it is, it's lighter because the hydrogen peroxide bleaches out the blue jean, okay? But it's still got hydrogen and oxygen only. This time when they did the ratios, it came out to be 16 to 1. So not 8 to 1, 16 to 1. There's more oxygen in hydrogen peroxide. And the real numbers, again, go back to periodic table. 2 times 16 is 32. 2 times 1 is still 2. 32 divided by 2 is 16 to 1. But that means that this substance has twice as much oxygen as water compared to hydrogen. Okay, that's the law of multiple proportions. They can happen to have this, well, we'll get into the definite proportions. They always have the same proportions for the particular substance. I was jumping my guns there. Okay, so again, it's just about the masses because that's all I could measure, right? We didn't get agreement. These guys didn't get agreement even in their lifetime that matter was made of atoms, although Dalton came up with that, the next person we're going to talk about. And but it led to that concept. Okay, we could explain this if the little oxygen pieces were bigger than the hydrogen pieces, which they are. Okay, so each element has a different size atom. All right, and the gentleman, of course, that came up with the idea of atoms was John Dalton. And he said that those same 2 elements can make multiple different compounds. And so it's just like, some people call this the alphabet law, just like 26 letters in our alphabet can make thousands, millions of words. The same ones rearranged. We can do the same thing with the elements that we have. Okay, and so the law of multiple proportions. Elements can combine in simple whole number ratios in multiple ways. There's also multiple proportions. Different multiple ratios of proportions to give different results. New compounds, new characteristics, same elements, just differently. Again, the same letters in the alphabet can make more than one word, depending on how you put them together. Okay, and of course, the cycle around is something more interesting. Let's talk about brownies and cake. The same ingredients, flour, sugar, cocoa powder, eggs, butter can make brownies, or they can make cake. Okay. You put them together in different proportions to get different results. Same thing with our chemicals. Same two elements can go together in different ways. Crazy stuff. Here's nitrogen with oxygen. I think I talked to you about it last week. 5 different compounds that only have nitrogen and oxygen in them, but in different proportions. 1 to 1, 1 to 2, 2 to 1, 2 to 2, which if you reduced it would be 1 to 1 again, but it's heavy, and then 2 to 5. How is that even possible? Well, if you look at the masses, and again, these are using the masses that are on the periodic table, 14 for nitrogen, 16 for oxygen. This one has 14, this one has 14, this is 28, 28, 28. All the nitrogens are multiples of 14. So this one has 1, this one has 1, this one has 2, 2, and 2. Okay, oxygen, 16, 32, 16, 32, 80. Do the division. 16 divided by 16 is 1. 32 divided by 16 is 2. 16 by 16 is 1. 2. 80 divided by 16 is 5. So these numbers down below, when we get to that simplest reduced proportion number, those become our subscripts in our chemical formulas. Okay, and that's how chemical formulas came about. There's equal proportions of nitrogen and oxygen, even though they have different masses. There's twice as many oxygens as nitrogen. There's twice as many nitrogens as oxygens, etc. Same kind of thing with carbon monoxide and carbon dioxide. Again, same 2 elements combined in different proportions, make very different compounds with different characteristics. This is another diagram from your textbook. Just looking at the orange and the teal color bars, 5 grams to 2 grams, 5 to 2 ratio for A and B, make-believe elements, 10 to 2 in the other compound. This compound has twice as much A as this one. 10 divided by 2 is 5 to 1. So instead of 5 to 2, it's a 5 to 1 ratio. So that's just another example of proportions. Okay, one other weird thing, and I just have to emphasize this because it was a sticking point for myself. You know, a ratio is just a fraction, right? That's super easy. We also call them proportion. So all of those words kind of mean the same thing. Ratio, proportion are probably more closely related than a fraction. If there's a denominator with units that's only units in it, like price per pound, if you go and buy some broccoli or something, it's so many dollars per pound. The per pound part is always understood to be 1. So for example, gas is $3.59 a gallon. I think that's what I just paid this morning. $3.59 per, you know how to read that slash line as per. And we usually just say per gallon. You need to understand that's 1 gallon. So that whole using the dividing line as a slash line, that's to make all the typeset go in single line instead of having to use multiple lines. For our purposes, I'd like to get in the habit of doing your fractions horizontally so that you would have the $3.59 on top per 1 gallon on the bottom. Okay, and that'll be important in just a sec. All right. Everybody got a calculator? Hopefully. Somebody got a calculator? Let's try this really quick. That's for tomorrow. I'm going to pick on somebody. Justin. It's fine. Would you just read?
Okay. Lead forms 2 compounds with oxygen. One contains 2.98 grams of lead and 0.461 grams of oxygen. The other contains 9.82 grams of lead and 0.763 grams of oxygen. For a given mass of oxygen, what is the lowest whole number mass ratio of lead in the 2 compounds?
Excellent. So that sounds awful. There's numbers or something with a ratio, lead and oxygen. What's the symbol for lead? Pb. So compound 1 has this much lead. Compound 2 has this much lead. And obviously everybody knows oxygen. Okay, so the first thing you're going to do is find the proportion of lead to oxygen. So everybody do this, 2.98 divided by 0.461. I'll pick on somebody. And then we're going to do the same thing for this one, 9.89 divided by 0.763. So these are more realistic numbers. Nothing really obvious at this moment, I would guess for most of you. Cade, what'd you get?
For the second one, I got 12.96.
Good. 12.96. Awesome. You guys know that you can do Desmos on your Chromebooks and have a calculator there too. Anybody have this one? What'd you get? Oh, go ahead. Either one of you.
You go.
CJ? Huh?
6.46.
Good. So when there's only 3 numbers in that you're dividing, you only get that many in here. We really should only have, that could be 13. We'll leave it there. Okay, it's fine. So what do you notice right away? This compound versus this compound, which one has more lead in it relative to oxygen? This one, right? And do most of you see that this number is pretty close to, this number is pretty close to twice this one? Right? 6.46, 12.96. You know, just kind of estimating. That's, if I divide those, I should get a number really close to 2. And you do. And you can prove it to yourself if you like. I'm just going to tell you it's 2.01. So what that means is this compound has twice as much lead in it relative to oxygen as this one does. And that's, there's a couple of ways that oxygen and lead can go together, because lead can have a +2 charge, if you recall, and lead can have a +4 charge. And oxygen's always a -2. So if we look at those 2 compounds, one of them has, it's actually relative to oxygen, more lead, or more oxygen compared to lead. You could look at it both ways. All right. The last part of this is just talking about how to name things. So if you need a review on how to name things, I have a hard time with their graphic. Personally, it doesn't make sense, all that much sense to me, but I'm not a great one for graphic organizers. Some people are, but this is just like a naming tree, you know, yes or no, go this way, go that way. And it can help you figure out how to write the compound formulas or how to do the names. Remember, IDE endings are going to be binary compounds. Ide or ate have polyatomic ions with oxygen. Prefixes in the name is going to mean you're having a binary molecular compound, covalently bonded. If there's Roman numerals in there, that's because it's a transition metal, or like lead, that could have a multiple charge. And so this is the other tree that's at the end of chapter 9. And if it's useful to you, great. If not, that's great too. Questions? All right, you're a lively bunch today. Is the testing taking it out of you?
Yeah.
Really? Was it hard doing the writing?
No, it's just time-consuming and brain
Time consuming and brain frying. Was it like a full length test, or did they cut it down? They're supposed to cut it down.
It's the writing portion, so we just do like one like smaller question that leads into like the essay paragraph. So it's just like,
Oh well. Well, at least it's over, right? Okay, so turn in your notes right now, please, with your data, please. Make sure that that's submitted, the stuff that we just did, and we'll call it a day. There'll be assignment for you, obviously, for tomorrow. Have a wonderful Wednesday and a wonderful rest of your Tuesday. I think I'm done. Did I turn off recording? Stop recording. There we go.